thanks to the NXP people who told me about this conference. It's fun to be here since I'm a relatively new member of the Zephyr community. I became interested in Zephyr about 1.5 years ago now for this particular project. And I'll sort of start off by saying this augmented reality project I'll talk about has kind of been a long-running thing, and I've gone through several prototypes. I'll be talking specifically about one of the more recent designs that I did. So this presentation covers up about until mid-2023 in my prototyping journey on this project. So in this case, my sort of overall augmented reality project has a few major goals. I started it mainly just because I wanted to learn about low power mobile electronics. I want to try to make something very small and lightweight, which can serve as a wearable computer with a near eye display. So you'll see photos of this in the slides later, but you know, it's a wearable device. It has a display, various processing capabilities and sensors. So I wanted to try to make this, you know, as close to phone level display capabilities as I could. You know, I want to try to see, you know, could this be a useful device for showing complex graphical information, you know, perhaps referring to notes, viewing maps as you walk around, and just experiment with those sorts of potential applications. So initially, you know, it's monocular. It has a display for one eye, kind of like Google Glass was initially. It's this sort of lightweight augmented reality idea. Now, in my previous prototypes, I had been using embedded Linux systems. Some of the previous talks I gave years ago about this, you know, I focused on using an MPU from STMicro, that STM32MP1. So I had a design using that. You know, I was trying to sort of achieve these similar goals, and eventually I got sort of frustrated with the MPU approach of doing things and always using embedded Linux. You know, first, I'm always dealing with DRAM power consumption. You know, having an external memory device with a, you know, very fast, complex interface also sort of restricts your board design opportunities, makes it harder to miniaturize. So you end up having to use system in package or package on package devices to get the design as small as I want it. And of course, this won't be covered in this presentation, but optical design and mechanical design of such a device is a, you know, whole world of other engineering challenges. Here I'm mostly focusing on software considerations bringing Zephyr into this project. So when I decided, let me try an iteration of this prototype using sort of one of these crossover MCUs, or these sort of crossover processor that has been showing up with more advanced multimedia capabilities than traditional MCUs, why would I choose to run Zephyr on it? Well, initially, I want to be able to move as fast as I can in this prototyping process, because being a side project, I always have limited time, and I want to, you know, quickly get an idea, you know, what can I make work? What's the farthest I can push this quickly? You know, where are the points of most resistance? So to me, I was quite happy moving to a Zephyr development workflow from my sort of embedded Linux background. I felt like the whole build, debug infrastructure with West was, you know, easy to understand and set up. It's very appealing to have a collection of drivers to refer to, so that your job bringing up a new board is easier in a lot of cases, or you have reference code to take a look at. And of course, the community surrounding Zephyr makes it appealing, especially in the long term. If you make progress on some new sort of esoteric element of your system, there's a hope that maybe it could be useful to something else, to someone else in the future. And you know, that kind of connects with the vendor independence aspect as well that's been mentioned in other presentations today. So first, I'll just give an overview about the particular board we're working with, and then of course there's the mechanical enclosure. But this arrived, you know, it was kind of designed late 2022, early 2023. It's 10 millimeters high, so it's this little board. And it essentially integrates, of course, the MCU in the center, which we'll talk about on the next slide, external flash for the code, display and camera connectors, of course, your various oscillators, power management stuff, some sensors, accelerometer, magnetometer, gyroscope, and a Wi-Fi module from Silicon Labs. Of course, there's a lithium polymer battery, single cell that it can charge. In this photo, it's covered by a black cap, but there's a USB Type-C connector on the right-hand side. And for those who might be asking about debug connectivity, so SWD in this case is exposed on sideband use pins of the Type-C connector in a slightly non-spec compliant interpretation of that USB debug accessory concept, which is used in some other commercial products. So the sort of main character of what I'm talking about today is this NXP IMX RT500 crossover processor. So it's a microcontroller with a large internal SRAM. And in this design, that's appealing because you can put it on a really tiny board like this. You get your microcontroller, but you also get MIPI DSI display output, so display controller and a DSI PHY. You actually get a 2D GPU. You also get the Tensilica Fusion F1 DSP, which is, a VLIW DSP with some cool instructions that can be useful for encoding, decoding variable length stuff. So it's appealing just because of this notion, oh, can I take a low power microcontroller system and push it to do those graphical things that my embedded Linux systems were doing? Can I connect a high resolution display to it? Could it be useful for this kind of wearable, where I want multimedia and I want low power? So that's the motivation for taking a look at it. So just to get started, before jumping into all of the problems, of course, that I run into bringing up something like this, we'll just start with some of the easier things. So of course, when the board arrives, power it on, connect it to the J-Link, and SWD works right away. So at that point, you can load code into SRAM and execute it from the SRAM on the chip. But if you're going to do a custom board with one of these IMX RT parts, and you have code in external flash, it's likely using this Flex SPI interface, which requires some configuration. So for instance, the eval board uses an octal SPI interface. It uses it in DDR mode. Of course, it uses different clocks compared to the part I have. So first, you're going to need to change this flash config potentially for the flash part that you use on your board. So we'll go back to the dark slides, hardware mode. So of course, take a look at the datasheet for the flash part you have on your board. Things like the sector size, properties of the blocks on the device matter. And while we're in hardware mode here, to get the board initially working in a sort of nice state to move forward, we also want to check a few other things. So the power management IC, the PCA 9420, which is specifically meant for this RT500 part, you can of course change properties of the regulators, voltages and such over I2C. So on my board, sort of to improve routing, everything is on a single I2C bus, which is the Flexcom 1 interface. So we're going to have to check that in the device tree to make sure we can talk to the power management IC and just get that fundamental thing out of the way. And then on this design, all of the I/O is 1.8 volts. So there are a few things we'll look at there as well. So going back to software mode, in this case, I have the flash config file with the requisite things changed. There are changes in this lookup table mechanism, changes to the clock, and the number of I/O pads used. In the board.c file that comes along with the board directory in Zephyr, for instance, for the eval kit or for your custom board, there are calls to the hardware abstraction layer for things like setting up I/O pad voltage ranges. So kind of step 0, make sure all of these are appropriate for your particular system. And of course, then enabling clocks for things that might not be present on whatever you're using as a reference. So for instance, if you're using peripheral IP or various blocks that don't have their clocks enabled, you have to make sure that that's happening properly when you're talking to the HAL. So those are just a few sort of small details that I just had to pay attention to bringing up a new board for the first time. And then you're free to organize everything nicely in device tree. So from this point, I have a board that can run code from the flash. I can do all the standard easy stuff with devices on the I2C bus. And then it was kind of time to move to the real problem I wanted to see if I could solve here. Can I take this little microcontroller system, drive the display I want with it, which we'll get to next, and see how far we get with these sort of multimedia capabilities in a low power system. So the primary challenge and what I found the most fun about this overall project is this display that I chose to use. So in these little wearable devices, of course, being space constrained, the amount of area you have for the display is also constrained. So this particular display is an OLED on silicon micro display, so it has a silicon backplane and then an active matrix OLED structure on the top. And the pixel density is incredibly high, so these are quite cool devices, also quite niche. There's not a huge amount of applications for them apart from these wearables and sort of emerging devices like that. This one is made by this Chinese company called Vuetrix. VTOS-6202, I believe, is actually the part number of their backplane and display driver IC that's integrated into the backplane. And then the manufacturing of the entire module is sort of a complex process of multiple other companies that confuse things a bit. But I refer to it as VTOS-6202. It has a MIPI DSI interface with either one or two 4-lane links. So you can use one of them or you can use two of them, up to 8 lanes total in parallel at the typical about 1 gigabit per second per lane. So that's so that they can do refresh rates higher than 60 hertz if they want and things like that. Some other random details that you find in the datasheet about it, you have to use the 24-bit per pixel packets in high-speed mode. You have to ensure that the clock is discontinuous, so the high-speed clock changes to the low-power mode of the clock lane in the blanking periods. So things like that, I ran into as problems along the way bringing this display up, and you just have to dig through all these tiny details of this, esoteric part and get it right. But that's part of the fun. This particular display runs in video mode, so you're constantly sending frames to it. If you've seen some of the other demos of RT500 low power stuff from NXP, one of the tricks that you can use is put a lot of the chip into a deep sleep state where just SRAM is retained and clocks are gated, power is gated, and so on in between display frames if your display can maintain its own image, but between those frame updates. For instance, if you only updated the display once per second. In this case, you unfortunately can't do that, or at least I don't believe that this display has any capability to do that internal memory sort of behavior. But in any case, just getting started with bringing up this display, well, the RT500 MIPI DSI PHY only has 2 lanes, so we have to figure out, can this display even support being driven by a 2 data lane DSI interface. The clock, according to the documentation, is limited to less than this 1 gigabit per second per lane that we might be accustomed to with most of the standard MIPI DSI implementations. And of course, what sort of frame buffers can fit in the onboard SRAM. Because on this particular board, I don't have external memory, like external PSRAM that they have on the eval board, and that's mostly to save board space. So I'm working with a certain set of constraints here, but I found that kind of fun just in the sense of seeing what can you do with limited resources. I find it forces me to learn about all the details in order to get things right. So there are a few points in our favor about getting this display to work. First of all, you can actually run the MIPI DPHY faster than specified in the documentation. It works at room temperature. Maybe you shouldn't do that if you're more serious, but I like to see what works. The actual display itself actually has registers which can select a smaller region of pixels to refresh. So this is cool because if you're viewing the real world and trying to display some sort of overlay, as an augmented reality device does, most of the pixels of your display will be black because black means, well, you're looking through to the real world. There's no extra light presented to the eye. So you could just say, oh, let me display a small image in some region of the display. I only need to write that much data out to the display. And then using registers on the display, you can tell the driver IC in the backplane to move that region of refreshed pixels around the display. So that's a neat trick that could also be used in an application like this. If you were constrained in terms of the DSI interface and you wanted to use fewer than the full 1920 by 1080 pixel display. Now, in terms of fitting buffers in the SRAM, you can fit an individual full HD frame buffer at 16 bits per pixel. Of course, with all of these, yes, you're restricting the amount of SRAM you have available for other things. But again, this is just what's possible if you push the limits. You can fit two 1080 by 1080 square frame buffers. And of course, if you were to use sort of YUV modes or 12-bit per pixel NV12-like pixel formats, which aren't yet supported in the Zephyr drivers for this particular display controller, you could get it down to 12 bits per pixel and maybe push it a little farther. The actual PHY, can fit, if you do that 1080 by 1080 square, you can get over 60 hertz out if you're using the slightly higher than recommended PHY clock, and around 60, 65 hertz if you do this reduced refresh area of the display. So this is kind of promising, because it means, there's still things I can do. It's not sort of hopeless to get this, fancy little obscure display to work with this microcontroller, even though perhaps if you just take one glance at specs and data sheets, it might seem so that it might be a very a poor fit, but it's possible. So there are more problems. As you can see in the photo, it does work, but before you get to it working, there are more problems. This particular display, of course, there's almost no documentation about it. You have to write this gigantic set of initial settings to registers. Some of them are lookup tables for things like gamma correction, color correction, various brightness curves, and essentially none of them are documented. The sellers of this display and the manufacturer will just give you this blob of writes to do using display command set in the low power mode of the MIPI DSI interface. And they say you have to use the hex 39 packet type, which is the display command set long write, to do all of these register writes. Now, typically you wouldn't do that. Typically you would sometimes use the short writes, but they want you to do them all using this long write. And that actually doesn't work in NXP's HAL because it breaks if you try to do a write with only 2 bytes using the long write packet format. It's actually easy to fix. It's just like one-liner change. But this took me like a month of free time to debug because I'm learning about this for the first time as I debug it. And in the scope trace here, you can see this is data lane 0 in low power mode, so it uses this sort of one-hot encoding. So it ends up treating the 2 bytes of data as the length, and then just reads tons of memory, dumping it out because it thinks it's writing something super long, a super long payload. So once you fix this, then the display works. So it's very, very exciting to see this work for the first time. And I kind of just enjoy doing things like this because then when you take a look at a normal, not terribly obscure MIPI DSI system or display, then it feels easy after dealing with things like this. So I found it a fun way to learn. So that takes care of display, and I mean you can see a little bit of interesting graphics on that disassembled photo of my device over there. The next thing that I wanted to check was, can I easily bring up a camera? So apart from the display connector, there's another of these little FPC mezzanine connectors for a display, which the one I chose is from Himax, the HM01B0, which is just a low resolution, like 320 by 320 sensor meant for always on applications. So this has one of these parallel interfaces, which you might have seen before, where there's 8 bits of parallel data out. It's clocked. There are horizontal and vertical sync signals. So if you read the datasheet for the RT500, it says, yeah, sure, you can connect this kind of parallel interface to FlexIO. And FlexIO is this cool peripheral with sort of shift registers that can be cascaded to form a sort of buffer. And then to get this data into or out of the FlexIO, of course, you want to use DMA. So there's this smart DMA engine provided in the chip. So you think, okay, of course, this should work, right? This should be fun. Now, the smart DMA has APIs that from Zephyr you can call to do various high-level things. So for instance, smart DMA is used a lot on this chip to move data from memory to the DSI interface or to other displays instead of the sort of more standard LCDIF display controller. But in this case, I want to go the other way, right? I want to use this smart DMA to read data in from the FlexIO to support this camera. So it doesn't have a high-level API for that. But it's a DMA engine, right? We should be able to make it do that. Well, there's actually a lot more to learn about what smart DMA is, and it's not quite as simple as just treating it like a DMA engine. So I found out smart DMA is actually this 32-bit programmable I/O processor, and it's designed to do things like keypad scanning, encoders, these sorts of fast I/O protocol decoding and things like that. In other places, it's called EZH. I found that name more, so I started calling it that. So really, I got into this, because, well, this is an obstacle standing in the way of me getting my system to work, right? So the display was quite nice and straightforward experience for the most part. This is a bit trickier. So in typical situations, a programmer just uses the APIs that the smart DMA engine firmware exposes. So there's a binary firmware blob that's loaded onto this smart DMA engine. The Zephyr driver says, okay, the user wants to use this particular API, which might be this, for instance, DMA endian swap. All of these, for instance, are moving data from memory to a display, or doing, actually some of them are memory to memory, like there's pixel format conversions and whatnot. But generally, you're only supposed to use these predefined APIs. If you want to do something else, like read data from a camera, which in 2023, when I was doing this, was not available in the binary blob. If you want to do something else like that, you're out of luck if you're a standard programmer. So, of course, I'm new to the Zephyr community, but in contrast to things like the display system, where I felt I had both, a nice, comfortable level of abstraction and a good view of what the hardware was doing, here it seems like what you see if you only look at Zephyr is, a far cry from what's actually happening in the hardware. If you only looked at Zephyr, you would think, maybe these APIs are actually implemented, maybe they're fixed function in the hardware. They're not. There's actually a firmware, and it is programmable, but the programmability isn't exposed to users at this point. So of course, going farther and further off topic from making an augmented reality device, I wrote a disassembler for the EZH instruction set. So you take this binary blob and, I've always liked to take things apart and know how they work, so I had to know how this works. So you can download the PDF of the slides if you want to look at the comments for a longer period of time. But this is, my interpretation of how this endian swap thing happens, and generally what I think is going on. So if you wanted to do something custom with this processor, there's actually a header, FSL Smart DMA PRV.h, which you can use to essentially assemble these sorts of instructions back into binary just by compiling it, because they're like macros, essentially, which are defined in that header. So this is what you have to do to get this camera working on this board, right? So that's kind of an example of one part of this development process, which wasn't as quick or as low resistance to getting this sort of system up and running with Zephyr, because you have all the niceties of Zephyr, but then you have mechanisms like this under the hood, which can stand in the way of this sort of system being simple and easy to bring up. So more recently, you know, I haven't like gone all the way to having examples of code of my own that actually runs on this processor, because this particular camera, HM01B0, can actually output a serial stream just like normal SPI, and you can just go back to that if you just want your frame data and you don't want to deal with this Flex IO, because then you just feed it into a normal SPI peripheral, use standard DMA, and you're done. So with these low resolution cameras, you can do that, you know, but sometimes these sorts of mechanisms can be troublesome. So in terms of the overall project, these are just some photos of this sort of mechanical assembly. In this enclosure, this board, you know, is in one side of the enclosure essentially, and then there's room for the battery in the other side. Currently, of course, optical design being a big challenge, this just uses a very simple optical system with 2 biconvex lenses so that the display is focused correctly kind of beside your nose for the right eye. So it was, you know, an interesting sort of journey. I find it always an interesting journey to go all the way from, you know, designing a board to doing, you know, software bring up and then doing the best I can with my mechanical design and limited optical engineering skills. So then in terms of like what can I do with this system? Well, apart from using the display and you know, moving about within the limited camera functionality we get without being able to, you know, program EZH ourselves, there are some other fun things. Of course, since the board has accelerometer, magnetometer, and gyroscope, you can do sensor fusion nicely and get the orientation of the user's head. So that's often a pretty fundamental thing in augmented reality and virtual reality applications. I also experimented a bit in the past with, you know, using accelerometer data to detect, you know, the user tapping on the device, which could be used as an input method, you know, and of course, looking around forms of, you know, an input method to change what is shown on the screen. For connectivity, this Wi-Fi module I have on board from Silicon Labs, someone, you know, had a pretty well developed driver which wasn't merged yet. I haven't checked on the status recently, but it wasn't too difficult to get Wi-Fi running and use Zephyr's network stack to connect, in this case, to an Android phone. I used using Wi-Fi Direct, and then do fun things like, you know, shuttling data back and forth, showing content from the Android phone screen on my wearable device's screen. I did a sort of very simple video codec just to get that working, sort of minimum viable, which just takes into account things like solid filled areas, scrolled content, so you only send what's new, and cases like that. Big areas where I think more progress could be made. This chip, of course, in addition to the Cortex M33, has the Tensilica Fusion F1 DSP. So it has quite a few fun instructions for variable length decode and encode. So I think you could implement some nice sort of coprocessor functionality on that for handling data compression and decompression if you're sending sensor data off the device or receiving video data wirelessly to the device. So that might be a fun way to learn about interprocessor communication with the sort of mailbox mechanism and Zephyr's support for that. The other fun thing on this chip would be the GPU, which I haven't really looked at yet, but in a lot of these sorts of applications, if you, for instance, render a frame on a device like your phone, then you transport it to the wearable device, by the time it's received and decoded on the wearable, the user's head position may have changed. So then, for instance, you could use the GPU to warp the image accordingly for the newest data that you have on board from the inertial measurement, your accelerometer and gyroscope. So that's a pretty common thing in these VR, AR wearable applications. Of course, designing optics is a big area in which I'm still learning. And there might be some potential to do display systems with 2 displays, one for each eye. But I don't have content about that yet at the moment. So kind of in summary, hopefully this kind of sums up my experiences using Zephyr to, try to make progress on this, very ambitious long-term AR project. So some systems on this board are very easy to get going with Zephyr. Of course, when you're initially bringing things up, you have sensors like these inertial sensors that have existing drivers. It's very easy and convenient to get those going. Things like the display, it takes some digging, but I think Zephyr provides a good framework in which to do that digging. I found it really enjoyable to learn about, new aspects of maybe DSI I didn't know anything about before, using Zephyr as a tool to develop this system. The, I think, biggest takeaway that I feel like became clearer in my mind working on this system is that in a lot of cases, specialized peripherals are very important in getting the most out of your silicon. In this case, if you have some very nice specialized peripheral which can do exactly what you want without burdening the CPU, well, yes, it's very convenient, but only if you're able to utilize it. So in the case of the EZH or Smart DMA, well, it's not going to help you if you can't program it. So in a lot of cases, users do want a simple picture, because if they're doing something simple, they don't want to think about all these details. But advanced users then can't get the most out of their hardware if the advanced features are hidden down, in the HAL, behind a binary blob, and so on. So I think those sorts of considerations could potentially become more important in the future. I know in some cases, new AI or ML accelerators will have one or even multiple dedicated sort of management processor units running a firmware in order to schedule things onto execution units, and in these AI and ML workloads, well, you could just take a high-level model and say, yes, please run it on the hardware, but then perhaps in some cases you want much more fine-grained control over what this embedded management processor is doing. So that's, I think, just something that at least I think I'm thinking about into the future. What's the best way to expose these sorts of complicated, dedicated hardware peripherals to users from a software point of view? Because they seem to be showing up more and more. Things like this EZH or dedicated coprocessor peripherals with sort of specialized abilities. So that kind of sums everything up. I know it could potentially be a lot of content and disjointed, complex content from many different avenues of this project. But if you have any questions, I'd be happy to answer them. Thank you, yeah.
First of all, people like you inspire me. I love that you've gone in and dug in this deep. Is there a sort of an open group, a team working on this as well? And if so, how do you sort of engage with them? How do you keep the whole thing going as a group?
So this project has just been my personal project. Really, I was working on it in college just as a side project. And this particular iteration of the prototyping, I mostly did, senior year of college. So in terms of like software development in Zephyr, there have been a few, patches and pull requests I contributed back so far to fix minor things with this, but there isn't a group of other people working on this project along with me right now. Of course, the broader Zephyr community has really helped make things like this possible. Like for instance, the display drivers and various things like that showing up at just about the right time for me to start using them in early 2023. But I don't have like any direct collaborators on this particular bit of hardware right now.
Thank you.
Two questions. First one is, in one of your slides, you have a big asterisk saying there's a long story on how you figured out all these documented register settings. Could you go a little bit more into that? And the second question is that you designed the board before working out all the numbers on whether you can like actually make everything work, or you kind of have a good idea on that, like it would kind of work before. So yeah.
Okay, yeah, so I'll answer the second question first. So when I designed the board, let's see, I designed and fabricated the board without knowing how to configure the display for two-lane MIPI DSI mode. So yes, I took a risk in fabricating this board that the display would not work at all, because this particular register setting that's hard to find for this display, if it didn't exist, the multiplexing of data over the lanes wouldn't be correct. You can't just connect two data lanes and have it work. So yeah, I essentially did fabricate the board before having everything figured out. Things like what you can fit over the interface, I think I had checked on that briefly. I hadn't really, looked into it in detail and done all the fiddling with, resolutions and blanking that the display is happy with. So yeah, I try to make myself take more risks with designs because I feel like they work too often. Yeah. And in terms of like the long story, so a lot of it is, me emailing back and forth with various Chinese sellers who are selling these displays, trying to figure out, who knows about the actual display driver IC on the backplane. So there was a bunch of reverse engineering I also did about the registers. This was in like end of summer 2022. I was like fiddling around with the registers of this display, dumping them all out. There's a company, Novatech, which makes display driver IC IP blocks that go into display driver chips. And some of the registers have some similarities to what you can find in Novatech datasheets publicly. And then there's some article, I forgot where it was. There's some reference somewhere on the internet to this company, Viewtrix, having some dispute with Novatech. So it seems like it may be similar to some of the display driver ICs from Novatech, but it doesn't match up exactly with them. Like there's stuff in these big initial register settings that they'll give you that isn't anywhere in Novatech datasheets. So I don't have documentation for it. I just happened to find someone who would tell me what register to set. Like, they didn't give me a data sheet. They just told me set this register to this value. So yeah, it was a long journey, but I suppose part of the moral of the story is it helps to get better at talking to people.
Thanks for the great talk. And I'm just wondering how many revisions did that board require, and also were there any lessons that you learned from designing such a small board that packed, everything on it?
So this particular sort of long and narrow board, I've done two, so the initial one and then a second revision. It was just to fix a few minor things related to this Wi-Fi module. Everything like display and all the sort of basic stuff worked on this first iteration. So this was sort of the first board I did, which is so tiny that you have to use high density interconnect stuff like blind microvias. So it's the first board I designed with those sorts of techniques. But it's not being hand assembled by me, of course, because I find it takes too long for me to try to do that. So it's my exposure to like the assembly considerations is limited because of course I just design it on the computer and it shows up at my door. Of course, yeah, there are a ton of new board design techniques I learned by doing this sort of thing. And though this presentation was of course focused on software, that's a significant motivation for me to do this project as well. Yes, it's just to learn about more modern PCB design techniques and microelectronics details.
So you had some objectives on your project about low power and stuff like that. So how did you get to the point of trying to, one, measure, but then figure out how you can tweak things, or especially with respect to what Zephyr might provide to you and also this part that you were using?
So yeah, I have done power measurements on this system. I don't have them sort of collected in a nice format to present. Essentially, if you have the display on at reasonable brightnesses, so that it would be, viewable outdoors or in bright overhead lighting. The display power consumption quickly dominates the overall power consumption of the system. The other thing, which is really sort of a major contributor if you're sending lots of data, is Wi-Fi, especially if you're transmitting. The actual MCU, of course, while there are a lot of techniques you could use to save power in sleep and various things, simply decreasing your display brightness, saves you more power. So I didn't go super deep into looking at that yet. I'm sure there are some savings to be made there, but for instance, if you were able to sort of compress things more effectively and send less data wirelessly, I think that could potentially have a larger impact. So yeah, I haven't gone very deep into looking at that yet. I suppose a contributor to not spending a ton of time on that yet is the fact that with this display, I have to refresh it all the time, so the part can't be put into the deep sleep with SRAM retention. But you could power some other things down probably.
So thanks for the talk. This is really cool stuff, honestly. Did you, with the display, was this kind of the only display that could do it, or did you look for a display that could do command mode so you could get away with going into low power modes like that?
I haven't seen one of these OLED micro displays with like internal frame buffer memory. Maybe they exist. I haven't found one. Apart from like this particular series of displays from this company, Sony also makes a lot of these micro displays, but they use the LVDS or FPD link interface, which is not maybe DSI, of course. So it would not really be possible or easy to use them with this MCU. So yeah, currently this display is really one of the only options that kind of fits what I want to do here in terms of its size and resolution.
Was just wondering, with the smart DMA engine, are these binary blobs just being handed down from on high in NXP, or is there actually some sort of compiler where, users can generate their own things? Is this kind of an NXP or a Zephyr issue?
They're just handed down from NXP. Yeah, so I suppose the question that comes up is perhaps how should Zephyr deal with situations like this, which is a question for the more experienced people than me. Yeah.
Questions?
One other question for you on the wireless part. So I sniffed around and looked. It looks like the pull request is using SPI for that. Did you look at switching it to SDIO? Because I know there's SDIO on there, but I'm assuming you built it out over SPI and you're locked in now, right?
Right, yeah. So on this board, I only have SPI connected, yes. Of course, yeah, SDIO would be more ideal in terms of getting it faster. But yeah, for this module, I only did SPI.
Thanks. Any more questions? No? Well, thank you very much. Thank you.
Thank you.